All right, let's start. Okay, so we will continue to study on LU factorization. Okay, so far we discussed about the overview of LU factorization. So LU factorization takes any size of a matrix, not just a square matrix. So you can take this short and fat matrix or long and thin matrix as an input, and then it factorizes it into a product of the two matrices, and the first one is always the square matrix. Okay, this square matrix, and then the second matrix will have the same size as the original matrix. Okay. And then this is called LU and L in U, and our U is echelon form matrix that we will get from the first phase of Gaussian elimination. Okay, so you can think of some pivots like this, and then we can think of this staircase shape. And also, we can have some pivots like, this, in this form. And then our L, from the definition of LU factorization or condition, it should satisfy unit lower triangular matrix, which is, given this square matrix, it will have the diagonal entries as all ones, and then some non-zero values in this lower triangular part, but on the upper triangular part it will all have 0. Okay, so that is called unit lower triangular matrix. Okay, and then given the input matrix A, we considered its elementary operation in the form of matrix multiplication with our elementary matrix, right? And then, as I mentioned, for example, if we need 10 operations, as I mentioned last time, we when changing the matrix A into U, which is a echelon form, not the reduced echelon form. Okay, so the echelon form, when making the echelon form, the only type of a row operation that we use is row replacement. Okay. Okay, and then here the point that we want to make is each of our row operation corresponding to some row replacement will also be unit triangular matrix, unit lower triangular matrix. Okay, and then the whole product will also be unit lower triangular. And also, we understand that each of these matrices is invertible, and also when moving it to the right hand side, and then it can be represented as E1 inverse, E2 inverse, which reverses the order, and then taking the respective inverse matrix of it, and then E10 inverse, and then U. Okay, so that's how we obtain the LU factorization, where L is corresponding to the product of inverse of our row replacement elementary matrix. Okay, and so here again the point is E1 through E10 is still unit lower triangular, and their inverse yeah, we can also see see its inverse as well. I mean, it's just an overview that we will study during this class. But the point or our conclusion after studying or understanding all the details of this LU factorization is that yeah, each of these inverses is unit lower triangular, and more interestingly, when combining them as a product of whole matrix, will also be unit lower triangular. So that's how we obtain L. Okay, so that's a brief sketch about what we will discuss today. Right, then let me just directly go to the exercise. Okay, so suppose we are given this matrix, and then yeah, let's just try to make it echelon form matrix. And then let's imagine the first step of what we do. So this guy will be our eraser, and then which one do we erase? These guys, right? And then let's imagine multiplying some elementary matrix that will perform this row replacement that we will do in the first step. Okay, so from here, yeah, the first equation will remain the same after performing one step of a row replacement, which is 3, -7, and -2 and 2, right? And then these will be 0, right? Okay, and then how can we make this guy 0? Okay, so in this case, yeah, we just moved, I mean, we kept the first row as it is. So what will be the first column from the perspective of row combination perspective? So in that case, it will be 1, 0, 0, 0, because that will be the corresponding linear combination coefficient. So again, we have 4 different rows, and then this guy, this guy, this guy, this guy will work as a linear combination coefficient of these 4 rows provided in the right matrix. That's how we perform or understand this elementary matrix for the row replacements that we do. Right? So 1, 0, 0, 1, 0, 0, 0. And then what about the second one? Okay, what about the second one? Okay, the second one, the new second one can be represented as, so this is the first row, second row, the third row, and the fourth row. And the new second row is the first row times what? Negative, or yeah, let me write it in this form. Minus or negative, and 3, and negative 3 over 3 plus the second row. So does it make sense? So basically, we just figure out, or we compute the ratio between these two values, right? And then take the negation of it. So I'm gonna rewrite it in this form, and minus. Okay. Right? So what will be the corresponding linear combination coefficient? Minus, and this guy, and 1 and 0, 0. Right? So let's just call this guy as A, B, C, and D. And then what is this value? It is negative B over A, right? B over A. So that's the value that we multiply with the first equation and then add it to the second row to make this value as 0, right? Right? And then what about the third row? Okay, what about the third row? Can we still make, or can we perform this row operation to make all the lower entries in the pivot column of this guy, or the first columns, when can we make all the lower entries as 0 simultaneously by just multiplying this matrix just one time? Yeah, it is possible still. So in this case, how can we represent this the new third row? It will be the first guy times what? This guy, and plus the old third row, right? So we have 3 and we have 6, and so we multiply it by 2 and then subtract it from the third equation, right? So how did we obtain this 2? 2 is basically the ratio between A and C, right? So this guy is minus and 6 over 3. And then what about the remaining columns? Remaining rows? 0, 1, 0. Because this is corresponding to the original third row, right? Right. And then what about the fourth one? So you will see the pattern: minus, negative, and 3 and minus 9. 0, 0, 0. Oh, sorry. Right? So at least this row replacement is unit lower triangular, right? So we all have, we have all ones along the diagonal, right? And then, it is it has a additional kind of special structure, not just beyond unit lower triangular, because this part is non-zero, right? And then this part will remain 0, right? Okay, so from the overview of this figure, so you can see kind of pattern, or how this E1 is formed, right? So it is starting with identity matrix, right? So we start with the identity matrix, right? And then when performing the first step of a Gaussian elimination, those values will only be the only non-zero entries, and this part 0, this part will also be 0. And then how can we fill out, or how can we determine these values? They are simply the ratio. Okay. So so B, C, D, and divide it by A, right? And then take the negation, right? So this is our E1, okay? And then we will obtain the new matrix as an intermediate output of Gaussian elimination, right? And then suppose this guy is our new eraser. So this is our new eraser, and then we have to make those start values as 0, right? And then it's an so let's just set it. So let's assume that our eraser was computed as maybe 4 and maybe 3 and -5, for example. Okay, so this is 4 and 3 and -5. And then what will be our E2, which will still perform the row operation. Okay, and using this, we will erase these guys, right? And then let's think of the corresponding L2 that will be multiplied on the left of the intermediate result. Okay, so in that case, we can see kind of a pattern. So it will start with this elementary identity matrix. Do we change the first row? No. How about the second row? Do we change it or not? So let me show some Gaussian elimination example. Is there any? Right. So here, okay. So here, okay. So after making all of them as 0, right? And then this one will be our eraser, and then we will erase this guy, right? By using this example, how can we represent our elementary matrix that will erase this guy? By using this as an eraser. So it will be 1, 0, 0, because the first row will not change at all. And then what about the second change that contains our eraser or the current pivot that we have? It will not change at all, right? So that will also have 0, 1, 0, right? And then now we will just, so we will have 1, and then we will just fill out this as non-zero entry, because the new third row is like this guy times what? Negative 3 over 2, and then add it to the third row, right? So it is 3 divided by 2, and take the negation of it, right? So that's how we make the second elementary matrix of E2, right? So here, so if we obtained this intermediate result, and then we can easily see the patterns, like, so this one will be 0, 1, 0, 0, and then this one, so we will only touch upon those values as non-zero values. So what is the first value? It is 3 divided by 4, and then negative. And then negative 5 divided by 4, and then take the negation of it, right? And then 0, 0, 0, 0. That's it. Does it make sense? All right. So in this case, when performing this only the row replacement, and then we can see the patterns of, non-zero entry, the patterns of the positions of these non-zero entries for E1 and E2 and so on, right? And also here, in order to be able to define the LU factorization, not all the matrices, in the case of, not all the input matrices can have a LU factorization. So some matrix may not have LU factorization by its definition or the requirement. So some matrices may not satisfy the requirement that is needed for LU factorization. Okay, so it's like the solution for AX is equal to B does not always exist, right? For some matrix A and B, vector B. Okay, so likewise, for some matrix A, LU factorization may not be defined or may not exist at all. Okay, so what is the condition that guarantees the existence of LU factorization of a given matrix? So that is when performing this row operations. When performing this the row operations on this matrix, we are only allowed to use row replacement. But when do we need some other types of an elementary matrix? So this is when we sometimes need like row interchanges. So as an intermediate result of a Gaussian one step of a Gaussian elimination, what if this value, instead of 4, what if we see 0 and 3 and negative 5? And then inevitably we have to perform row interchanges to bring non-zero element into our pivot position, right? So for example, the third or the second one should be interchanged with the second one, right? So in this case, if your matrix requires this kind of row interchanges, that's when this LU factorization is not defined or doesn't exist. Okay. Then why is it so? Why is this so? Because because our elementary matrix corresponding to row interchanges. Okay, so if you remember this, that this guy is the elementary matrix corresponding to row interchanges between the first and the third one, right? And so you can see that like this guy and this guy, yeah, is actually, yeah, having the one over here. Okay, so is this elementary matrix satisfy the unit lower triangular structure? So it is not a unit lower triangular, matrix, because we have ones in the upper triangular part, right? So that's when we violate the condition that L is a unit lower triangular matrix. Okay, so in that sense, we just assume our matrix don't need any of these row interchanges during the entire process of Gaussian elimination, until obtaining the echelon form matrix. Okay. So in other words, while performing this Gaussian elimination, we don't need any of row interchanges, meaning that we don't see any of these zeros in the eraser position. Okay, so we will always see non-zeros in this eraser position. Okay, and then we can safely assume that our sequence of row interchanges, sequence of row replacement, will be represented as E1, E2, and so on, right? And then each of them will have this kind of pattern. So suppose your matrix has maybe 5 by 8, for example, and then E1 will be like 5 by 5 matrix, right? And then 1, 1, 1, 1, 1. And then E1 will have the non-zero entries over here, okay? And then what about the E2? E2 will have 1, 1, 1, 1, 1. And then this part will be non-zero entries and 0, and 0, and 0. And then what about E3? E3 will have non-zero entries over here, and 0, 0, and 0, and 0. Okay. All right, and then to understand that we can obtain, we obtain this L as lower triangular part, which is the product of inverse of each elementary matrices. Okay, so let's consider the inverse matrix of each elementary matrix that we used to perform row replacement. Okay. So the point is, let's see. Right, if you remember this, okay, then this is a kind of a simpler row replacement example where we just added the first row times 3 to the fifth row, and then replace the old fifth row with this new representation, right? And then in that case, it is like 1, 1, 1, 1, 1, and then we only changed the last row, right? And so the original one and the first one times 3, and then added it together, right? So this was a kind of simpler example where we also see like a 0 over here in this case, because we didn't change, or we didn't apply any row replacement on the second, third, and fourth, right? Okay, so in this case, we consider this an inverse, right? Inverse, to revert this new matrix back to the original matrix, right? And then here we also considered the second step of elementary matrix multiplication, right? And so if you remember this, and then given this a new set of rows, And then can we represent this linear combination of the new rows to reconstruct each of our original rows, right? And so from the first through the fourth rows, it didn't change at all, so we can safely use this 1 0 0 0 and 0 1 0 0 and so on. But what about the last one? So these are the the new coefficient applied to the new set of rows given over here to reconstruct or recover this old fifth row, right? And then you guys remember this, and then let's look at the pattern between these two. So simply the inverse of it is represented in this form. So we have 3 over here, right? And then here we have -3 over here. So that is our inverse, right? All right. Similarly, when performing this, let's see. Okay, so this is the first step of a elementary matrix performing row replacement. And what will be the inverse matrix of it? So can you imagine the pattern? The inverse matrix will have this result. 1, 1, 1, 1. I'm going to just give you the result, but here you know the pattern, and negative and b over a, negative c over a. When we have a, b, c, d, right? And then this guy is negative d over a, right? And its inverse matrix is similarly just taking the negation of these values again. So instead of having negative sign over here, we just simply remove them. Okay, so negative 3 by 3, 6 by 3, 9 by negative 9 by 3, and 0 0 0 0 0 0 0 0 0. Okay, so this is our inverse matrix of this row replacement matrix. Okay, so let's understand why it's true. Okay, right, the new second row. So again, the new second row. So let's denote it as 2 prime as the new second row is the old second row minus b over a times old first row, right? That's how we make this guy as 0, right? Right, and then from here, how can we represent the old second row as the linear combination of the new rows, right? So in this case, we can, I'm just doing the same thing that we did in order to obtain this inverse matrix of it, right? So in this case, b over a times 1. Here, 1 is old one, right? But we need the linear combination coefficient for the new ones, new rows. But here, the first row didn't change at all, so the new first row is the same as the old first row. So it can be represented as this one, right? And so simply, the only difference is found over here by taking the different sign of it, flipping the sign, right? And then we can do the same thing on the third row. So the new third row is the old third row minus c over a times 1, and then and then this guy is our inverse of this row replacement operation of this guy, right? Does it make sense? Any questions so far? 다 이해가죠 이거? 시험에 나올 가능성이 높은 거예요 이거. 네. Okay, so yeah, at this point, so far we understood how we can form each of our elementary matrix, and now in order to obtain this L part, okay, L part, we need actually the inverse matrix of row elementary matrix that we applied in the process of Gaussian elimination. And then from E1, we can see its inverse matrix is obtained as just by taking the negation of those non-zero entries, right? That's how we obtain this E1 inverse, and also obtaining the E2 inverse. That is the same process. So given this matrix, so this is E2, right? And then how about E2 inverse? E2 inverse just simply taking the flipping the sign of it, right? And that is the inverse matrix of this E2, right? So that's how we obtain E1 inverse through E10 inverse, right? And then let's think of the product of it. So right, let's take this example. So this is a E1, and then making them as a positive signs will give us E1 inverse, right? And then this guy, we obtain this, and then this is our E2 inverse, right? By just flipping the signs of it, right? Okay, and then, just to help you understand, let me just utilize this. Okay, so this is our A, and this will be our eraser, right? And these will be the values that we erase, right? And then what is the corresponding E1? It will be 1, 1, 1, 1. And then what about this value? Okay, so we put negative sign over here, and negative 4 divided by 2, which is this guy, B over A, right? I'm just writing it, and C over A, and D over A, right? And then how about its inverse? Right? So simply, we don't even need the negation originally. We just make this guy divided by 2, this guy divided by 2, this guy divided by 2, and that's it. Okay? Right. And then this guy is the second, the intermediate result. And then what about our E2 that we multiply on the left? Let's make it as E1. So this is our E1. Then what about E2 over here? E2 is 1, 1, 1, 1. Okay, so 0, 0, 0, and 3 and negative 9. So we by default we have a negative sign over here, and then negative 9 divided by 3, 12 divided by 3, and 0, 0, 0, 0, 0, 0, 0. Does it make sense? So it is simply the ratio between, this guy divided by 3, this guy divided by 3, and then take the negation of it, right? All right, so this is E2, right? And then we can easily compute E3 based on this guy, right? This is the second, the second intermediate result, right? And so here, let's compute E1 inverse as like this guy, and E2 inverse as this guy, right? And then let me just rewrite it. Right, so this is a, and then we have some u, although we have another matrix over here corresponding to E3. Yeah, so yeah, let me just rewrite, yeah, write it fully. So what about the E3 over here? E3 is 1, 1, 1, 1, and 4, and divided by 2, and then take the negation of it, right? Okay, then let me write it. Then right, so this is E3, right? Okay, and then let's try to obtain L. So L is E1 inverse, E2 inverse, E3 inverse, right? And then what about E1 inverse? What about E1 inverse? E1 inverse is simply 1, 1, 1, 1. Then we have these values, right? And then take the negation of it, right? Right, so 4 divided by 2, 2 divided by 2 is negative 6 divided by 2. Okay, and 0, 0, 0, 0, 0, 0, 0, 0, 0. Right, so that's E1. And E2 is 1, 1, 1, 1. And then here, yeah, we simply remove this negative sign over here. So negative 9 divided by 3, 12 divided by 3, and right, and then 1, 1, 1, 1, and then 4 divided by 2, and 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Okay, so here, yeah, one kind of interesting magic happens over here when computing the product of it. Okay, the product of these inverse matrices of these row replacement matrices, okay, is even without computing their product, I can just write their inverse matrix. That is 1, 1, 1, 1, and we just bring it to this part. Then 4. And then we also bring it to this part. And also we bring this. And that's it. We don't need any computation. Okay? So that's how we obtain L. So let me just simplify this operation and then show how we can easily obtain L over here. So over here, yeah, these are different Gaussian elimination. Yeah, these are the process of Gaussian elimination. Right, and then I mean, we will still have to perform this Gaussian elimination, okay, and then have to obtain U part or echelon form matrix. But in this process, we can just fill out our L as the final result, which is like L is what? Given this pattern, okay, so 1, 1, 1, 1. It's a little bit small, but this guy divided by 2, right? We don't need any negations, minus sign over here. So minus 2. So 2 divided by 2, right? That's it. And 1. And negative 6 divided by 2. And minus 3. And then we move on to the second, this intermediate result. And then here, this guy divided by 3, right? So minus 3. And this guy divided by 3, 4. And then this intermediate result, and then this guy is pivot, and then this guy is the one to erase, and so the ratio of it is just 2, right? Then this is our final L. Okay? Any questions so far? Right, and then so we didn't prove the product of all these can be written as this form, even without having to compute anything. Okay, so yeah, if time permits, I will prove it. Yeah, after explaining more important part first. Okay, so yeah, where is the LU factorization used, or where can this guy be useful? In what applications? Okay, so in the case of an LU factorization, yeah, so suppose you are given the same matrix A but different B part. Okay, and then in this case, when computing is solution, and then we will just form the augmented matrix A and B1, and then we'll perform their own Gaussian eliminations, and then we will also perform its Gaussian elimination again for a new B2, right? And then here, yeah, you can see that the Gaussian elimination part will almost the same, right? Given the same matrix A, right? But here in this case, if we just perform the Gaussian elimination from scratch or from the beginning, given this, and from scratch, once again for this A and B2, right? In this case, yeah, many of these computations will be quite redundant, right? While performing the Gaussian elimination on the A part, because A part is exactly the same, right? So in this case, yeah, there are some redundancies in our computation, right? So at a high level, if we can perform our Gaussian elimination only for the A part, and then somehow it can be recycled. I mean, the computation result of this pre-computed Gaussian elimination only for the A part can be recycled for easily computing the linear system solutions when a different B part is given, like B1, B2, and B3, and so on, right? And we saw this situation exactly when computing our inverse matrix. So for example, in the case of an inverse matrix, as I mentioned last time, okay, so if you remember this example, so we are given it's a process of computing the inverse matrix of the given matrix, the given square matrix, and then suppose we want to obtain the second column, and then it will be the solution of AC2 is equal to 0, 1, 0, right? What about the first column? It will be the solution of AC1 is equal to 1, 0, 0, right? So here, exactly, we see the example of having to use A over and over, but with the different B part, 1, 0, 0, 0, 1, 0, and 0, 0, 1. In this case, we don't need actually to perform this Gaussian elimination from scratch, okay, repetitively. And how we solve these equations simultaneously, okay, can be done in this manner. So we just stack B1, B2, B3 as the augmented part, okay, and then we perform the Gaussian elimination on this single big augmented matrix that collects all the B's, B1, B2, and B3. We just simply concatenate them column-wise, okay, and then that way we can just avoid any repetitive computations, because in this case we will just perform the Gaussian eliminations only once, right? But what if we are not yet given for a new B, okay? So in the case of machine learning, So far we obtained maybe 100 people, and those 100 people's record works as a B1 through B100. Okay, but in the next day, tomorrow, we are given a new B, which is a B101, or like 101st person. Okay, in this case, as of yesterday, we cannot form this big augmented matrix because the new B will be given in the future, right? So in that case, there is no way to recycle this kind of computation, right? So redundancies seem to be kind of unavoidable, but that's when we utilize this LU factorization. So suppose we obtained this LU factorization of the input matrix A, and then suppose we are given any kind of B, okay, maybe tomorrow's B or the day after tomorrow's B, and so on, okay, and then we utilize this LU factorization that we already computed in advance, as follows. So okay, so A was already decomposed. We already obtained the result of LU factorization of the input matrix A that will be used over and over, okay. So in this case, we can represent it in this form: L and U and X, and their whole product is B. So in this case, let's imagine like this part, okay? So it can be viewed as X is first transformed by U, and then transformed further by L, and that will be resulting vector B, okay? And in this case, X is mapped by, for example, Y, by the linear combination matrix of U, which is appearing first, okay? And then through L, which output should we obtain over here? It is B, right? So starting from B, so it's like obtaining the corresponding input vector given an output vector of B from the perspective of a linear combination. So given B, right? And then we are given L and U. We know the full information about L and U. Then by using L, we can obtain Y first, and then using Y, by using the inverse mapping, or by using U, we can obtain X, right? And so it can be represented as L times Y as B and U times X as Y. Okay? So let me spend maybe 2 or 3 more minutes to finish up this explanation. So here, let's imagine we obtained this LU factorization in this form. So clearly, the given matrix A is represented as L, which is unit lower triangular matrix, and then the upper triangular matrix. And then from here, let's first obtain, from this figure, let's first obtain this Y by using L L and B. Okay, so L is again our unit lower triangular matrix, which is a square matrix, and our B is over here, right? And then from here, we will have to do still Gaussian elimination to obtain the solution, right? And so our solution will be obtained in this form by making this part as reduced echelon form or identity matrix, okay? And then this is what? This is the solution corresponding to this part. And then this guy is further used to obtain X, where we now use U part, okay? So we form additional matrix, augmented matrix by using U this time to map back this Y into X by using U, okay? So U is again upper triangular matrix like this, right? And then we obtain the final solution as an X. So in this process, so we computed LU factorization beforehand, and then we computed or solved 2 times of this Gaussian elimination, or 2 times of linear systems, right? L Y is equal to B, and U X is equal to Y. right? But in this case, we have to perform solve the two linear systems, two different linear systems. But here computing the two different linear systems is really simple because of the structure. Because this L part is lower triangular matrix. So this is called the forward substitution. So let's imagine it's a linear system version. So what is the linear system corresponding to the first equation? It is like x1 is equal to -9. We have no other variables over here. So it is really easy, right? And then let's plug in this -9 over the second and the third and the fourth equation. And then what about the second equation? It had two variables, but we already know the first variable from the first equation, and so we can easily obtain the second variable's solution, right? And then it is plugged into the subsequent equations. And then what about the third one? It involves three of the variables, but the first two are already obtained, and so it is really easy to obtain the third one, right? So that way, even though it seems to be, it looks like a complicated linear system, but it is actually not because of the structure of this unit lower triangular matrix. And in the case of an upper triangular matrix as well, we can do the same thing. So here, which equation has the fewest number of variables? The last one. Last one had only one variable. So in this case, we can easily obtain the last variable's value, and then we just plug in that value into the upper equations, and then move to the upper equation, and then plug in this guy in, we will obtain this guy easily. So that is called the back substitution, because we just obtain the single variable first by using the last equation, and then we substitute that variable into the upper equations. So this is how we perform this LU factorization and utilize it into the linear system. Okay, so the time's up. So I strongly encourage you to just do your own exercise by just solving some exercise problem in this chapter of 2.5. Okay, because that is covered in our exam. Okay, that's it for today. Thanks.
죄송한데 뭐 하나 좀 여쭤봐도 약간 수업 외적인 거긴 한데
네.
이제 저희가 두 개의 매트릭스가 곱하는 상황으로 볼 때 이 A 왼쪽에 있는 매트릭스 입장에서는
네.
얘 콜럼 벡터들의 선형 조합이 될 거고 결과는 B 입장에서는
네.
로우들의 선형 조합이 되잖아요. 근데 이게 보니까 그냥 A 매트릭스의 벡터 하나랑 그 순서에 맞는 B
네.
매트릭스의 로 하나를
네.
곱한 것들의 총